All right, so we've been talking about limits. Limits does lots of stuff for us. We use them a lot. One thing that they help us to define is the concept of continuity. Okay, continuity, we're going to discuss today, and you guys are going to help me come up with a rigorous definition of what it means for a function to be continuous. Okay? So if I've got, let's talk about continuity on an open interval here at first, right? So if we look at some function, something like that, where we're going from A to B, let's start with a really informal definition, and then see if we can come up with something that's a little more formal, right? So what do you think it means to be continuous on an open interval? Go ahead. What do you? Well, okay, just the last part, don't worry about the last part. For a function to be continuous, open interval just means it's going to be, between A and B. But say it again. Okay, no break in the function. Okay, that's true. That's definitely a requirement. What else? Anything else?
No holes.
No holes. Okay, good. That's a requirement. Say that again. There's a defined
point wherever you go.
Okay, so every point between A and B, the function is defined for all those points, I think. Is that what you're getting at? Okay, good. Those are pretty formal. I mean, you're kind of working towards our formal definition. What is it in terms of just my ability to draw one on the board up here? Think about that. If it's a continuous function on the open interval from A to B, then when I draw it, what's true about, when you watch me draw it, what's true about the act of me graphing that function?
You don't pick up your pen.
I don't pick my pen up, right? My pen stays on the board the whole time. Okay? That's it, right? If I don't pick my pen up, then it's continuous, right? Now let's think about how we could do this a little more mathematically. We have the concept now. It's easy, right? But how do we pin that down mathematically? I like what Seth was saying. He was saying something about for every point on the interval, it's defined. Well, let's go a little further than that. What has to be true for every individual point? There's an infinite number of points on this interval, right? But in math, a lot of times what we want to be able to do is we want to be able to say, let's take a random point on the interval, and let's define the conditions for that random point, and then apply it to all the points between A and B, right? So let's pick a point like C. Some value of x between A and B called C. And so that corresponds to this point right there, right? Okay, well, let's just kind of go through the list of things that you told me, and let's come up with some mathematical criteria that are going to make those things happen. Let's start with the easiest one, just that the function is defined there, right? So what does that mean? And if we wanted to say something like, let's kind of start a rigorous definition, and we'll just fill in the blanks as we go. So if we were to say something like, we're going to call this point continuity. And we'll say something like it keeps doing that. Is continuous at C. Okay, that's big. Continuous at C. If, and only if, what? So condition 1, the function is defined, right? How do we say that mathematically? If a function, if it's f of x, and we're talking about the point C, how do I say a function at C? f of C is defined. right? So when the ant, that's telling us, in terms of our ant analogy, that an ant with an x value of c is standing on firm ground. He's not in some black hole somewhere, right? I mean, he's standing on the function someplace, okay? Is that enough? Okay, let's come up with one example why that's not enough. Why is it not enough just to be defined? Somebody want, you can draw it if you want, or you can tell me whatever, or tell me how to draw it. What do you think, Nick?
Because what if it was defined on the line, and what if it point?
Okay, good. So what if it did this? What if it did something like, if that's C, oops, that's open, and then we had a point up there somewhere, right? The function is defined. Make sense? Clearly it's defined, but the ant is, I'm going to have to pick my pen up. What's another way we could shoot that one down? Well, say, go ahead, somebody, go ahead. Breaking the function? Yeah, we could do this too, couldn't we? If that's A, and that's B, right? Make sense? Okay. So it's a necessary but not sufficient condition. Yes, sir?
You describe it as being greater than or equal to A and less than or equal to B, so it's within the parameters of B. So it's not defined somewhere else along the y-axis.
Say that again. I didn't follow that.
Okay, so it has to be between A and B essentially along the line.
Right.
It can't go higher or lower than the A and B y values.
Okay. But what if, okay, I see what you're saying. Can somebody think of a counterexample that's going to show that that's possible and still have it be continuous? Okay, so what if it did this? What if we had A there and B there, and we're starting there and ending there? But that's okay, isn't it? See what I'm saying? Okay. So we need some more stuff, don't we? Right? We go back to our list. That's a good start. It has to be defined, right? It has to be defined, because if it's not defined, we could have a hole there or something, or an asymptote, right? So it definitely has to be defined. That's important. What else do we need?
What I'm trying to say is, we have to say there has to be a limit of C or something.
Very good. What if we went back to this example right here, right? The problem with this one is that the limit doesn't exist at C, because the ants approaching from either side are anticipating different values, aren't they? Does that make sense? Okay, so then we'll go back to our list, and we'll add the condition. The limit of f of x as x approaches C exists, right? Does that make sense? So the ants have to think, they have to approach the same value from either side. Agreed? Okay. Which one of these, though, still is a burr in our saddle here? It's still not working. Yeah, that top one still isn't working, is it? Because the ants both approach the same value, but the function is defined somewhere else. So what's the last step we need? What do you think?
The limit is the same as the defined.
There you go. Okay, so the important step is this one, right? The important step is that the limit of f of x as x approaches C equals f of C, right? I would argue that this last step is sufficient because it implies the existence of both the limit and the value, right? Does that make sense? So technically speaking, all three of these are supposed to be provided, but if you start with number 3, the other two are obvious, right? That doesn't make sense unless the limit exists and the function is defined, right? Does that make sense? Okay. So then we can take our, now that we've got that, right, we can take, where's our picture? Oh, there it is. Okay, so how could we extend this idea then? This is the definition of point continuity. So how could we take what we just did and extend that to a broader definition of continuity on the open interval from A to C? What could we say to take our definition of point continuity and make it a little broader. What do you think? We showed that it works at C, but now how can we take this idea and define the informal concept of me not picking my pen up between A and B to mean the function is continuous on that open interval? What's our strategy again? We kind of mentioned it. We defined what the requirement is for the function to be continuous at a single point. How many points are there between A and C? But, infinite number of them, but if each of them observes these rules, then what? For every point between A and C, between A and B, for all values of C greater than A and less than B, if those conditions are met, then doesn't it have to be continuous? You see what I'm saying? Does that seem, I want you to kind of just ponder that for a second. That's what we do a lot in math. It seems like a tall order to say, okay, all infinite points have to obey this, but it's not that big a deal, because really what you're looking for are any violations of these rules, right? If there's a single point on this interval where one of those three conditions is not met, then it's not continuous at that point, and it's not continuous on the open interval, right? Does that make sense? So like in the book, the language of the book is, where does it say this here? Something like this. Consider an open interval I that contains, so here's our open interval I, right? It's just this. Right? Just the open, everybody knows that means open interval, right? The values of x greater than A and less than B, using interval notation, right? So if we're considering that open interval where x is greater than A and less than B, if the function is defined every place on that interval, then what do we get here? There's got to be a place where they... Oh, here it is on the first page. A function is continuous on an open interval if it's continuous at each point on the interval, right? So all values of C between A and B, if this is true, then it's continuous on the open interval, okay? Makes sense, okay? What do we do, though? Does it make sense? Give me a 1 to 5 on that. 5 meaning, yeah, sorry, that makes total sense. 1 meaning, what did you just say? That makes no sense at all. Okay, flash me up. Okay. Okay, so for the benefit of everybody in here, then somebody else take a try at that. Say it differently. If I want to define if I want to define continuity on an open interval, we just define point continuity. How do I extend that concept? Say it in different words while I write this down. Be brave. Somebody who flashed me a 5. State why it's a 5 for you. How would you say this concept? Well, I write this down. Come on now.
I think an open interval displays point continuity, but they're not doing any of those things.
Okay.
So it's just,
Well, keep going. I like it. Keep going. I won't interfere. Nick, I've never known you to not have something to say. Come on, say something here.
I flashed before.
What's that? Oh, okay.
Wait, so it is continuous if it doesn't, so it will always be continuous unless it violates one of those rules?
Exactly. Yeah, that's a good way to say it. It's always going to be continuous on this interval as long as there are no points in between A and B that violate one of those three conditions. Does that make sense?
Yeah.
Okay. So this is the book's language. And I really this needs to be very clear to everybody before we go further. So this is the point, this is the part that's if it is continuous at each point on the interval, right? That make sense? Another way to restate that, using, we could write this a completely different way. We could say a function is continuous on an open interval a to b if there is no point on the open interval that violates the requirements for point continuity. Okay? Same thing, exactly. I prefer the second definition. It's easier to look for a limited number of counterexamples than to think about, ponder the idea of an infinite set of points that meet a condition, but they mean the same thing. Okay, what if the open interval extends not from a to b, but if the open interval extends from negative infinity to infinity? Then what do you think we call this? Any ideas? Is everywhere continuous. Okay? There's no place where I'd ever have to pick my pen up off the board. All the way from x equals negative infinity up to positive infinity. Okay?
It's not continuous everywhere, it's everywhere.
That's the way you say it in math, yeah. I mean, you could say it probably either way, but that's the way you always see it. Math jargon. Okay? So let's define a couple things that we're going to build off of this, right? So everybody's okay with this idea then? So we got this concept of continuity on an open interval based on the idea that all the points in between A and B have to obey those rules, right? Okay, so what if we want to fill in the endpoints? So now we're going to take the same idea and we're going to define continuity on a closed interval. Okay? So it seems like a pretty minor thing, but we have to add a whole new concept to make this work. So here's our picture now. Almost the same picture, only this time we're filling in the dots at the end. Ideas. Now think what we did before, and let's just extend our thinking. And a lot of this it's not very algebraic, it's logical. We said we defined continuity on an open interval in terms of continuity at a point, right? So we took a simple concept and extended it to an interval. Can we advance the same kind of thinking to define continuity on a closed interval? What's the difference between the closed interval and the open interval? Okay, it includes the endpoints. So what's our thought about how we could maybe define this? A function is continuous on a closed interval if what? Okay, so it's continuous on the open interval, right? We've already kind of defined that. So it needs to be continuous on the open interval from A to B, but also what else?
Including A and B.
Okay, including A and B. That's the sticky part, right? So we've got to take our open interval. We've already got all the infinite points between A and B. We just need those two extra ones. How are we going to do that? They're not going to totally fit the criteria from before, are they? Because which part of this is not going to work at an endpoint? The limit, right? The limit part's not going to work, is it? How come? Okay, the ant can only walk to the endpoint from one direction, and a limit implicitly relies on the notion of approaching from both directions, right? So the concept of a regular two-sided limit just doesn't work anymore, but we mentioned this actually, like I think before Roundup. I don't know, I can't remember why it came up, but maybe you remember. What do you suppose we're going to lean on instead of a regular limit here at the endpoints? Say it again?
Nothing.
Okay. We got it. Do you remember what we called that?
Special.
Yeah, it's a special limit. It's a one-sided limit, right? Where the limit only requires that we approach from one direction because we can't approach from the other direction, right? So this brings up this new concept of a one-sided limit. Is this all? You see how we're building this up though? We're just kind of adding stuff as we need it. Yes, sir.
So, would it be that when you write the limit, instead of saying just simply that when X approaches the point, you say like a certain definition of X as it approaches it?
Well, you're going to have to assign a direction that the ant's walking. Otherwise, it's the same. Exactly. From the left or from the right is what we say. Sometimes these limits are called, limits from the left or limits from the right. Okay. So we'd have to take something like, for example, at A. If we want a limit to exist at A, we would have to adjust our normal definition. Instead of saying the limit of f of x as x approaches A, I can only approach A from which direction? From the right. Now think about the right in terms of a number line. That's from the positive direction, right? So we put a little plus there, a superscript that's a plus. And you see what that's saying? We're approaching A from the positive direction. Okay? Does that make sense? If this is, let's just call that value L. So then the limit of f of x as x approaches A from the right would equal L in this case, right? Make sense? What about the other side? How are we going to deal with B?
And then
As x approaches B from the negative direction would equal, I don't know, let's call that P, just for the sake of argument, so we can kind of see what this, how we write this stuff, right? Does that make sense? Okay, so now we know what a one-sided limit is, right? Now let's apply it here to this situation. So we've got this open interval that goes all the way from A to B. How am I going to deal with the extra stuff at the endpoints? What do I have to say? If I go back to my open interval definition, how can I extend that? So what has to happen? Is that the page? Nope. That page. What would I have to say? Except at A and B, the one-sided limits exist, right? Does that make sense? So at A, the limit of f of x as x approaches A from the right exists, and the limit of f of x as x approaches A from the right equals f of A. Right? See what I'm saying? So we got to have this stuff for a closed interval. Let me just copy this whole thing. So for a closed interval, oh man. So we got all this junk, right? That's what defines, we got the open interval. Relies on this, right? I'll abbreviate it. For all C between A and B, that stuff is true, but for the closed interval, we have to include also plus, plus at A, why do I keep doing that? This thing, I never did this last year. We're going to have to rewrite this to say f of A is defined the limit of f of x as x approaches A from the right exists, and then the big one, they're equal to each other, right? Oops, as x approaches a from the right. Right? That make sense? So that's allowing us to just fill in this endpoint up here. I'll go back down, right? Okay, so we got all the stuff in between, but then we got a one-sided limit exists here, and the function has the same value of that one-sided limit. And then the same thing at the right side. It'd have to write a similar statement for f of b, right? So I don't think you even need to write this down, honestly. It's all, I'll give you a page number. It's in the book on page 70 in your textbook. Here, in fact, let me just do this. You don't need to get writer's cramp from writing all this stuff down. It's right in your book. It's right here. Right here. Oops.
We just look at the box and then change the to that.
Oh, yeah. I think I'm almost there now. There it is. Okay. So there's what we want right there. Everybody see that? Rather than writing all this stuff down, let me just grab this thing and we'll... Okay, is that right? Yeah. Oh, darn it. There we go. Doesn't this say everything we were just talking about? Definition of continuity on a closed interval means it's continuous on the open interval, right? And this additional requirement that the limit of f of x as x approaches a from the right exists and is equal to f of a, right? And at the, that was the left side, at the right side, we've got a one-sided limit from the left of the function as x approaches b equals the value of the function there, right? Make sense? Okay. All we had to add is just those 2 extra points. Okay, last issue then. And there's not a lot of stuff, honestly, to do in this section. It's more about just understanding it. What about the types of discontinuities? Let's just describe these real quick. So we would say that if I've got some function we call that a point discontinuity. Okay. It's a discontinuity because I have to pick my pen up, right? Why is it a point discontinuity? Because to repair it, all I have to do is add a single point. This would also be a point discontinuity because in that case, all I have to do is reassign or move a single point, right? So if a function, if a discontinuity is reparable by either moving or adding a single point, that's easy to do. That's point discontinuity. Okay? In our textbook, they do this a little differently than the online textbook, so I'll just explain the differences. There are minor semantic differences. In our textbook, which is frankly a better textbook, let's look at these 2 cases. What if I have something like this? As opposed to an asymptote. Our textbook would call both of those infinite discontinuities. What does it call them exactly? It calls them point or Yeah, I think it calls it infinite. So removable or non-removable. The other way we describe this when it's a point discontinuity, we also say it's removable. Because I can remove it by reassigning a single point. These are combined are called non-removable. In either case, I would have to move an infinite number of points to repair the function, and so that's not, that's not possible to do without completely redefining the whole function, right? So those are called non-removable. In our book, they just call them infinite discontinuities. In the online book, they call this example right here a jump discontinuity, where it's not infinite, and they call this one an infinite discontinuity, right? Minor stuff, right? Not that it's a big deal, but when you look at the problem sets, they're going to refer to those differently, and so I want you to be aware of that. But the big thing is, non-removable, I have to move an infinite number of points. Removable, I move or reassign a single point. Okay? Once again, it's all in the book. All right, so what kind of stuff do we do here? Let's maybe close up with a problem. So how about something like this? A lot of theory, not much stuff we're going to do with that theory. Where would... Okay. I want you to tell me for this function a couple things. Are there any discontinuities, and if so, removable or non-removable? What do you think? Yes, sir.
I think there's no at the.
Okay, so the function is undefined at 3, isn't it? Right. So we know that x cannot equal 3, or f of 3 is undefined. So clearly then, what's the answer to part 1? Yeah, there is a discontinuity where at x equals 3. Yeah. Yes. Right? It's a big one. Is it removable or non-removable? Which one? How come?
It's only 1 point.
Okay, it's only 1 point, but let's think about the graph of this, right? If I were to graph this, it's not the fact that there's only one x value. How many points would I have to move to repair the discontinuity, right? This looks like, this goes like this, doesn't it? If this is 3, it's going to do something like, right? We wouldn't. We'd have to move an infinite number. And so this one is non-removable. Right? You see why? Okay, let's compare that to something like this. Can I move? I'm recording this. You can go back. I'll put the notes up too. The notes, did you notice the notes are all up for calculus now? The lecture notes? Okay, how about something like this? Oops. Oops. Accidentally picked that one there. Make that 10. There we go. How about that one? piecewise function. Right? This is probably about as far as I want to go today with this. We'll add some more teeth to this idea later. But if I were to graph that, how would I go about graphing that? How do you graph a piecewise function? Because we graph each piece individually on its interval, right, on its domain. So let's color code this thing. Let's make this 3, and this will be the yellow part of the function. So what's that look like? It's got a slope of 2, y-intercept of 1. So it's going to do something, would you agree, something like, sort of like that, right? What are the coordinates at that point right there? 3, 7. Okay, so those are the coordinates of the whole, right? Just, I'm going to cheat here because this is going to be inconvenient to graph, so I'm going to make that a 2. Sorry. Oops. And let's make this one red. So what are the on that piece? It's only defined at x equals 3. Excuse me. Oh my gosh. The value there is 2, so I get that one single point with coordinates 3, 2, right? And now let's move on and graph this one in blue. That's the horizontal line. Oh, I did that backwards. I'm going to cheat again. Let's change these signs around so I have to change my whole graph. Let's define this interval when x is less than 3 and that one when it's greater than 3. Same idea. Okay. So then this guy, if I graph it in blue, that's just a horizontal line at x equals 7, like that. Everybody agree? Okay. So what about this one then? Same questions. Is it continuous?
No.
So where is it discontinuous? At 3. What kind of discontinuity is this one? Point discontinuity, so removable, right? Because all I'd have to do to repair this, just reassign it. All I'd have to do is say, no, let's redefine that to be 7, right? And just one little repair, and it's now continuous. Big difference. I can't do that. If I go back to this one, I can't. I'd have to change. That function is fundamentally not going to work. It's infinite. If I want to make this continuous, I got to scrap the whole thing and write a new function, right? That makes sense. See the difference? How much time? When are we at here? 35? Okay. Let's try maybe one more here. Okay. I'm going to leave you off with this one. We're not going to get through this, but I want you to at least think about how you would approach this. Okay. Okay, so you can do this informally, probably right now, but I want you to think about, for tomorrow, I want you to think about how we could formalize this process. So let's take a function like f of x equals the piecewise function x squared when x is less than or equal to 2, and ax squared when x is greater than 2, or x, make that x cubed, and ax squared when x is greater than 2. Okay? So that's cubed. Okay, now just think about that for a moment. How could I want to pick, in this case there is no b, it's just an a. How could I pick the value of a to make this continuous? What has to happen? And just be concept. You don't have to think about any of our fancy definitions of point continuity. Just in basic language here, like you're describing this to a non-calculus student, what would have to happen? Right, say it again. Okay, now you're thinking way ahead. That's what I always have, because you guys are also smart. I mean, you're telling me exactly what A has to be. Just in general terms, what's going to happen to the two pieces of this piecewise function for this thing to be continuous? They're going to have to meet, aren't they? They're going to have to be equal, right? It's not going to be a gap. They're going to run into each other, right? Okay, and you're already thinking in your mind, okay, how do I make that happen? Well, yeah, x cubed would equal x cubed if A equaled x, which is 2, right? So A would equal 2, right? Does that make sense? Okay, so you know those things have to meet. Now let's think about this in terms of point continuity. How do we meet those 3 criteria? Okay. Well, the point that we're interested in is at x equals 2, right? And so the limit of the function from both sides would have to equal the value of the function, right? Does that make sense? Okay, right. Now, what is the value of the function here? What is f of 2? It's 8. How come? You're right. Okay, because it's included in the top domain, right? And f of 2, it would just be 2 cubed. Good. So f of 2 equals 8, right? We don't even have to worry about this side. Would you agree that x cubed on its own is continuous? Right? So the only part we have to be concerned about is the behavior of that side, right? So what's the condition going to have to be there then? The limit, right? Because that can never step on 2 on this piece of the function. The limit's going to have to equal 8, isn't it? Right? Now, what kind of limit is that going to be?
One-sided.
One-sided from which direction?
From
the right, because this is the function that's defined to the right of 2. Everybody agree? Okay. So we would have to say this has to be true, and the limit of f of x, which in this case is ax squared, as x approaches 2 from the right, has to equal 8. So really, this is the algebra equation that we're solving, isn't it? If we solve that, we're going to get 2, right? Think about that. We're 10 more minutes and we're done with this concept. All right, I'll put another assignment up that you can start.